Hi folks and welcome. My name is Nick and I'm gonna be talking about fresh performance crimes today. Usually I present myself as a performance detective chasing stability crimes for many years and blogging about performance investigation in Making It Faster blog. But today I would like to present myself as a Ukrainian whose country was invaded a month ago. Today we will discuss the performance crimes, the methodologies, and maybe something extra. The performance crime that we will take a look covers the time first byte jumping over 2 seconds, and once we were reported in the late of September, we managed to bring it down to roughly half a second. If you were to resolve this problem, what would you do? You can buy a bigger box, you can get extra caching layer, you can bring servers closer to the consumer, you can switch to Kubernetes, you can change the recovery model in SQL, you can do lots of stuff, right? Who knows me would know that I'm gonna be talking about the investigation techniques and the first one would be the brief look at the random change. You don't measure anything, you just change something randomly and you hope it to work. And you pronounce the statement that it has helped very confident, and the confidence statement made by a professional spreads the confidence around. How come could it work? Because reliable way to make people believe in falsehood is frequent repetition because familiarity is not easily distinguished from the truth. Blame someone else? You are finding the system you're not responsible to. In our case, that client has third-party systems the solution talks to, and we can blame them. The site takes ages to load because of them. They will do the investigation on our behalf, would give us some evidence, clues, and then we could use that clues to blame someone else until the problem is actually found and resolved. You might be surprised how often that's used. Here is an image showing that we've experienced Redis timeouts, and the support team of one of the vendors have asked us to check Redis connection. So the Redis is the cause of high CPU and site becoming non-responsive. It's not vice versa for them. And when it's actually the same team that reached Redis team said, come on, Redis was not on fire at all. It was not even requested. That's how blame someone else works. In that specific case, it was the critical section that we will talk about slightly later. So, in performance investigations, no random changes. We make a hypothesis why that is slow, prediction, like if we change something that's going to change one way around or another way around, test it, prove that it helped or no, and then repeat. So, that's what given for today. Time to first byte is over 2 seconds. What are we going to do? First one is to build understanding how the overall time is spent in between, how it is observable from the client, then on the server, and then how much time is spent in the cruel network by transmitting the signal. You might have guessed that servers could be far away from the client, and it's even true if we have the content delivery server and XDB database is somewhere else. So basically that's time as well. In our case, we have analyzed that and we found out that on client side, the DNS lookup takes astonishing 1/3 of a second. 1/3 of a second. A lot of time. A lot of time. Next, we jump to application insights. Pick random page. What is here is the heartbeat in Australia, and what we spot on here, a lot of requests to production web database. They are quite fast though, but it's the amount of those that in in total gives us higher response time. As you might have heard, I'm a fan of Purview. So what I'm gonna do next is to check the performance profile that we've collected. Purview uses discrete events and not only shows the call stacks that are sliced every millisecond, it also shows us the events from the runtime. And an example would be the requests that are waiting for session to be released. And if we compare our original IP, they are arriving from offender. So we can block that IP and that would resolve the first one. However, the next one, it takes 1.5 seconds just to load the home pages for sure in cache. How come? Let's see. I'll guide you through in here. So 45% of the time taken to produce the page response is spent in mapping the URL that you type in or just item path to item ID. Think about it. 45%, like almost 800 milliseconds. 350 milliseconds is spent on cleaning path cache that stores the caching for those item paths to ID. That's wild. And here we see the SQL request that we observed just now in application insights. Get child IDs by name. They are called a lot as well. That is the code that's actually getting executed, and I'll guide you through. First red line. If the mapping is known, then deal is done. Cool. The next one, we slice all the rel into parts and then trying to resolve it from top deeper into the tree. At one time, we find the ID. If it's not null, or if it's null, it's known not to exist, then we return null. If it is not null, we try to get the item definition with that ID. Just to recap, random point in time, homepage that is requested millions of times, for sure has all the data in memory, and cache remove mapping because the ID stored in cache doesn't exist. So why mapping cannot be resolved in here? Let's try to see. Who knows me would be sure that I'm gonna collect the memory snapshot whenever I can. And I have collected in this occasion as well. So let's inspect the item path cache content to see what's inside. Simple as that. And what we actually observe that the path is mapped to ID null. Please pay attention. ID in cache is not null. So the ID null with all zeros is attempted to get item definition. For sure it fails and it triggers the cache scavenge. So cache cleanup is costly, takes time, and then we also get the penalty next time of trying to find by name once the path is removed. Not in this run, but in the next one. Who could place ID null in there? The only use case from what we observe using reverse engineering tool like ILSpy or .pig or Reflect or whatever is the nexus, but it's obfuscated. Two ways. One is to inspect version 10 DLLs, no break-in changes, should work. Another one is use the obfuscator. Rain or shine, you'll see that it's actually the resolve path command and it adds mapping with ID null. So in this case, Nexus resolve path commands as ID null obfuscated the code, so it has no way for the rest of the kernel to know that ID null is legal. So in SQL provider, all is left is just to pay respect to ID null and know that it doesn't exist. Case solved, or wait a second, or no. At this time, we have found the culprit, but we still have half a second time just to give you the page markup, the HTML markup. Something that is like very easy to get. So on modern super powerful hardware, it takes half a second. Just think about it, half a second, right? Talk to your machine just to give you something you see in your browser. I'm gonna ask you about Moore's law. Hardware is expected to get faster 2 times every year or so. Like number of transistors should double. In early days, that was kinda true. Machines did not have a lot of computing power, like 33 kilohertz. Modern CPU would give you 3 gigahertz, and if you have 10 cores, it's like 10.3, so it's roughly 1 billion times faster right now than it was 60 years ago, 65 years ago. So if your software is not good enough, you cannot get the result. Basically, it was the clock frequency, the performance currency. You could scale the clock, you could add more transistors, you could do something and get more things performed at a time. Not sure if you heard about Dennard scaling. The idea is that whenever we make some technological progress, it is believed that transistor can be made 30% smaller. So 70% remains, and if we try to get the square, we need to multiply it, the area. And then it turns out that the area of one transistor is reduced by half, by 50%. Right? What it means that you could place more transistors at the same scale, and you can supply less power there, but the number of transistors grows. So it means that the amount of energy or the power density we supply at a constant growth would reach some surface, or at least was predicted to reach. So not only the transistor size should be reduced, but also the power it receives. But it is as was seen back in days like 20 years ago. What about now? Simple question. What I did for you just now, I took top tier processor for every year and I decided to compare them. Lots of numbers, but I'll make it simple for you. The throughput speed stays constant close to 5 gigahertz. That's as much as it can be achieved with the modern technology. What about the single thread rating? I think it's my image. You don't see the last number, but it's 2.7. Basically, in 5 years, the single thread has improved by 50%. Not 5 times, just by 50% in 5 years. And the multi-core mark has improved 2.5 times. Pay attention that the core speed, turbo speed, remains same, but the mark is greater. How come? Previously, there was one command to add one number to another one, and it took one cycle. But then you have the command that takes four numbers, and adds them in one cycle. So previously, you had to do 4 runs to add 4 numbers. Now you can do one. It's a simplified one, simplified example. But what it means? First, instead of adding numbers to single unit of computation, we put multiple cores in one processor, meaning that every core has separate caching layer and the shared, most likely, caching layer, right? And the performance gain can be visible only to certain number of algorithms that operate with pure data locality, meaning that the data fits single core, never leaves that. So basically, yes, in that case, you can get performance boost. In simple words, if you are using the general purpose algorithm that is not optimized, you cannot expect to get that big performance gain. As simple as that. If you just add something, it's like one cycle or even less than one cycle. But if you try to reach main memory, it's like 100 times at least slower. In one word, the version in Python or in Java, it's matrix processing, just written in normal fashion. And this is the speed up one. In Java is faster 9 times, but only with code that was written in specific fashion. When you got loops, you unroll them, you force the code to get the benefit out of vectorization, like the multiplies or the operations running simultaneously. Only then you can get a gain. Unfortunately, if I could put everything in one statement, I would say it as much faster CPUs is a sweet dream. Yes, processor caches grow. Yes, the number of cores grow. Yes, we get smaller transitions, so the number of transitions increase, so the number of commands processor can execute increases as well. We can, let's say, multiply not 4 numbers at a time, but 16 or more than that. But the truth is that in order to get that advantage, your code might be written in specific fashion, and the compiler must be aware of that. That's the reason why you need to stick with the latest compiler. So the question has to be asked, how to optimize that? You saw that pure program is 1, super optimized is 65,000 times faster. How to achieve that? What I'm gonna be talking today is Bentley's rules of optimization. We can either make better algorithms or we can try to change the amount of work to be done, or to avoid work that shouldn't be done, or to place the code somehow in optimized fashion. I'd like to bring your attention to the feature that has appeared recently. It's called Profile Guided Optimization. What it is about? The idea is that you have the data set that's going to be in production, in your real application. And you have a lot of places in code where it can flip one side or another side, but with the set of the data, it's going to go on the one way in 99% of the cases. By launching application multiple times and asking it to record how it runs, that information should be very vital, important for the compiler to make the decision how to work with the registers. Do we need to inline or not inline? If we for sure always use the last sealed method, why should we use the virtual call when we can do the direct call, and a lot of other things. So they aim high that. And what they're trying to do, or I've just explained that you need to first tell that, okay, please capture runtime behavior, launch it multiple times with the data set, and then make it built with the data that you have already collected. What it aims to do is to move from here, somewhere here. You see that the wins are huge if you do it the right way. Only if you do it the right way. There is a tiny disclaimer that it's only for native targets, not for CLR at the moment. I should have stopped my presentation right now, or no? Can we do the guided optimization on behalf of runtime? Let's take a moment and think about it. First one is to run the application to see how it operates. Second one is to know the data that it runs with. Third one is to know the path. The path is the logical branching where the code flows, which features are used or not used, and somehow tell that to your application. In other words, do we know the facts that are not reflected in the code? Considering Sitecore-centric idea is around items, the test scenario would be fair to load all the items and then just to see if I can read them without access result cache. It's empty, and then I just try to see if yes or no. Every Sitecore investigation lands in a situation where a big pile of time is spent in item level API. Let's expect it. The question that I'd like to answer is, can we make that API work faster? Not just 5%, 10%, but much, much faster. And ladies and gentlemen, the baseline is almost 9 seconds. Not bad to load the whole content tree and to see if we can read. Can read takes 7.5 seconds, roughly. What can be done? Before what can be done, we must answer another question. What are the challenges with the profiling right now? First one, it has limited accuracy. It slices the call stacks every millisecond. So if less than that, it's not visible. It just appended to parent operation. So if there is fast operation that's faster than 1 millisecond, it's not visible. And if we have 10 operations, basically we blame the parent one instead of the nested one. Second one is the observer effect. Remember that when we have more cores, software is expected to run in parallel or doing lots of things at once. And if we try to attach debugger to async processes, we will get 100% CPU. Because of debugger lock, the CLR internally attempts to grab the debugger lock that we saw previously. That's the critical section, and in our case, you see that's A9, just a lot of threads, basically. That's one. Two is application behavior changes when you have a debugger. Simple example, exception handling changes. Gets 4.5K, so basically 4.5 thousand times slower. What is left for us then? Let's go back and think about it. We have some facts that we know, but the system doesn't know, and we need to see what is the impact of sharing that knowledge into the code. First one would be always readable items. We're working on content management systems. Is it legal to say content management these days? Whatever. You have the Sitecore item. Isn't it fair to say that it's always readable in your solution? Then there is a home item, template item, and so on, so on, so on. Why would we force the system to resolve item access for every role user and parent? when we know for sure that item can be read. So this is the condition we know, but the system doesn't know. How can we get the list of items that are for sure always readable in our solution? We capture the memory snapshot, we check the access result cache, we see items that are always allowed, then we go to database. In database, we find all the items with the security field in it, right? And then we prove our statement that yes, these items are always readable, and the end result is expected to be something like that. There is an authorization provider that knows the system IDs that are always readable. Boom. Make a prediction. What would be the difference compared to the first run if we simply take this one optimization? 1 time, 2 times, 3 times, 4 times, 5 times, a million times faster. Boom. 38 times faster. Yes, gentlemen, you heard me right. As simple as that. Internally, there is an access result cache. There is a strategy to calculate the record size. There is a call to settings to figure out if cache is enabled, if how much time can we spend on calculating one entry. Then we need to make for access result explanation. So object allocate, and we need to find the object in cache itself. In order to find object in cache, we need to compose the key. So a lot of things under the hood. And it's performed for every role user in. Next one. Can we aim higher and try to make faster every item field read? So whenever you get an item, you get field.security or field.source or whatever field with the specific ID. If you think about it, item field is just the collection or the dictionary of items, of fields inside an item, and then when you get it by ID, it's no more than a lookup by a specific ID in a table or hash set or dictionary, whatever. How can we speed it up? Like this. Instead of comparing by value, the inner GUID that is inside the ID, we can switch to by reference compare, right? So instead of comparing the bytes inside the GUID, we can compare the pointer that's that. So if everywhere in our code we will have single object, field ID security, equals operation shall be 4 times faster. We can secure it by inlining or interning the exact ID in intern pool. Interning allows us to reuse same objects instead of producing new ones. You have an item, and every item we have created by field. When you read it from the database created by string itself or the field ID, the string is different. And then you build new ID every time, new object every time, but the ID is immutable, same as string. So the idea is to reuse that stuff, and we can bring this concept to a whole new level just by simply interning the IDs that are used everywhere. Reference instead of data comparison. My favorite sidecar settings used everywhere. That's the test case, the settings that are stored in memory, and the test is as simple as getting the time spent setting. Please pay attention that it needs the culture info in order to get the time spent setting. How it works in general. You have the setting switcher. It's the sidecar concept of the switcher when you have the context items. In context items, you build a string and you try to find in that hash table by the string. So some cost. It's definitely very low cost at a single call, but if you make millions of calls. That's not that fast anymore. Next one is cache. Cache must be thread safe. How the thread safety is achieved? Is it achieved using locking algorithms or no locking algorithms, like faster or not that fast? You can also pay attention that we had the culture info, and right now we don't have that anymore, right? We have just the parser, so this is the function. So the function holds the culture info, meaning that there is an object allocation, and again, allocation is cheap on object side, but if we make millions of allocations, not that cheap anymore. You're gonna be asking, why have I chosen time span? Because that specific one is used every time you want something to be placed in cache. So used like super frequently. 99% of the time you get these calls. Time calculation threshold. So recap. We have a few ideas that are not reflected in code, but we know for sure that this is the data load or the data access patterns, or how it's used, basically the guidance we should apply. One value read 99% of the time. In case of time spent, true. Settings are no longer modified. Yes. So we get 99.999% of the time. It's just read operation. We never change that. So we can guide runtime or code to be optimized for read dominance. And if we don't use setting switcher in our code, we don't need to pay the price for respect for setting switcher. And here are the results. You can see that the stock one is 1, and the optimized version is 8%, only 8% of that amount. Considering the stock version has also allocates that are hidden behind my picture in here, the values in runtime would be much faster. So instead of concurrent dictionary, we use the plain one with reference replacing. When we add the value, we make a copy of the original dictionary and then swap the value. So insert is expensive, but it's done only 1, 2, 3, 20 times at maximum. Secondly, we know that it's 99% of the time it's the cache size. So we can optimize it for single value. If the value is that, then return the value. That's how we get such drastic results. Next one, filter items. In Sitecore site config, you can tell if site will always show the current version of an item without publishing. That is needed when you have the live mode, so-called live mode. It's not used, as far as I know, these days, but the price is still paid. Every time you try to get an item, you need to figure out if preview or that filter item is enabled or no, and there is also the filter item pipeline. Filter item pipeline would involve touching Sitecore context. That is again cheap but not free, and if you scale it, it gives us a big pile of work. By simply moving it to site context doesn't have item filtering enabled, it can give us 2 times speed up just by a single line of code. And if we try to optimize it even further, we can remove the whole filter item pipeline or just leave one processor in there. It's gonna be big risk. With a few more tricks, we could get even to better results. We can improve the previous results 2 times. So in order to load the full Sitecore content tree, it takes 142 milliseconds. So instead of 6, or it was 7.5, and overall it was 8.6 seconds, we managed to reduce it to 0.142 seconds, or 60 times faster. 60, ladies and gentlemen. Yes, you read it right. Full content free, 60 times faster than stock. Just a few tricks, right? Next time you hear somebody complaining that backend is slow, we need to move everything to the edge. You have an ammo to say that backend is not slow. It's feature rich with the price tag for every non-used feature. You can do a lot, but you use small scope and you still pay things. If you can guide your code to disable not to pay the price for non-used features, you'll get super fast solution. Thank you for your time. What I'd like to mention is that you might have noticed that the images that I'm using in these slides are not the stock ones. They are from my personal phones and solely taken in Ukraine. For instance, the castle you see right now is destroyed. The city I visited last summer, Berdansk, is HD. The Dobropark near Kiev is under constant shelling and heavy fights. This Glampen is destroyed as well. The hard truth would be that neither prayers nor your flag in social media can stop the missiles that are damaging our cities and destroying them. While modern air defense systems that cost a fortune can't save lives. Thank you and hoping to see you someday in the future.